Okay, here we are, a week before spring break. Who's excited? Yay, yeah, we get a little week off. But before we get there, we have to finish this chapter and we have an exam. All right. So your exam is coming up on Thursday. All right. It'll open at 11. It'll close at midnight. There's an 80-minute time limit, unless you're on DSPS, in which case your time has been adjusted for whatever your DSPS accommodation letter calls for. Okay. But otherwise, it's 80 minutes. So make sure it'll close at midnight. So the latest you can start is about 10:30, right? 10:30 p.m. And if you want to have enough time to finish it before midnight. Okay. No surprises. Very similar to all the other exams we've had in this class. All multiple choice, all on Canvas, right? It's not an open resource exam. You can use the material I sent you, which is a periodic table and a table of contents. Table of constants. And you can use a one-page cheat sheet that you've prepared ahead of time. And you can use whatever resource you want to help you solve quadratics, but make sure you look for shortcuts, okay? 30 questions is correct. Most of them are worth 2 points. There's a few worth 3 points and one worth 4 points because some of them are going to take a little longer than others, okay? So I weighted them in terms of their point score a little bit more if they take more time. All right. We are going to cover, we're just going to finish the chapter on aqueous ionic equilibrium. Hopefully we'll get through all of it today. If there's a little tiny bit left, we'll cover that on Wednesday, and then we'll do a review for the exam on Wednesday. Make sure you check the email from me for this week, since this is an exam week, right? The assignment due dates and everything are just a little different than normal, okay? So make sure you have a look at that so you know when everything's due this week. All right. Before I get started, do you have any questions for me about anything?
Will it say on the exam what each question is worth? So
yes.
Yeah.
Yeah, every question has a point value and it'll say it. Okay. Any other questions? Okay, good. All right. So we're going to go over strong base added to weak acid. You saw a video on this already before coming to class, right? But we're going to go over it one more time because this is a tricky problem, right? And there's a lot of different parts to it, and I really want you to get it, okay? This problem, more than any, this kind of titration curve forces you to kind of integrate and call on all the material we've sort of been learning in the last couple of weeks. All right, so that's why different parts of this curve are a different kind of beast, and it's a really good review of all the different kinds of problems we've seen, okay? So first of all, whenever you do a titration, you should always ask yourself, what's the volume to the equivalence point, right? So this is gonna be, we're gonna have a weak acid in the beaker. I'm gonna go over this in a minute, but I'm gonna come back to this. But we're gonna have 25 milliliters of the weak acid HCHO2, okay? And we're gonna titrate that with a strong base, 0.100 molar NaOH, okay? And remember the volume to the equivalence point Oh, by the way, I got a new cable modem, so hopefully our issues are going to be in the past in terms of me breaking up. But if it does break up, would you guys let me know? Thanks. Yeah, I'm really happy about it. The volume to the equivalence point is always calculated by making figuring out moles acid equals moles base, right? So the first thing you figure out is moles acid, and that's always going to be equal to the volume of the acid, right, times the molarity, right? You're going to need this no matter what, 0.00250 moles of acid, right? HCHO2, right? So you know that. And then what's the volume to the equivalence point? The volume is how much base do you have to add to equal the same number of moles, right? Because the equivalence point happens when moles of acid equals moles of base. This doesn't matter if it's a strong acid, strong base titration, weak and strong, strong and weak, it doesn't matter. It's always moles acid equal moles base. That's where the equivalence point comes in, okay? You don't have to solve an equilibrium problem. You don't have to do anything for this part of the calculation. You just have to do straight volume to mole conversion and then moles back to volume conversion, right? So you know that to get to the equivalence point, if you have this much acid, you're going to need the same amount of base, right? Right? And you know the concentration of the base is 0.1 molar. Of course, I've picked the numbers here so that it comes out pretty easy, right? And you find out that that is equal to 0.0025 liters, sorry, 0.025 liters, which is 25.0 milliliters, okay? And that makes sense because the initial, the concentration of this is the same as the concentration of this, right? Which is also 0.100 molar, all right? So it takes the same volume because it takes the same volume to get the same moles. Yeah, this is the same problem from the video. We're just going to go over it one more time. Make sure you got everything, okay? 2, the initial pH, okay? The initial pH is the pH before you start doing anything. Well, before you start doing anything, what do you have?
You have a weak acid.
You have a weak acid, right? So how do you get the pH of a weak acid, and which equation do you use?
The Ba table, or
Henderson-Hasselbeck?
No.
Isn't that equation number 1?
It's equation number 1. It's a weak acid, and you just work an equilibrium problem, right? How do you find the pH of a weak acid, right? That's all you're doing here for the initial. So the initial pH, you just work a weak acid equilibrium problem, right? Forget even that you're doing a titration, right? Just a weak acid equilibrium problem. So here's your equilibrium equation, right? So you got HCHO2, right? I'm applying this to equation number 1 plus H2O in equilibrium with H3O plus A minus, right? And then you're going to do a ice table. And remember, ice tables, you always work in
concentration.
Ready.
concentration, right? I think I'm drilling that into your head enough, huh? I don't want to see any mistakes of working in moles in ice tables, right? Ice tables always in concentration. So you got 0.100 molar, 0, right? Minus X plus X plus X, 0.100 minus X, X, right? So then you got X squared over 0.100 minus X. And then you got to have Ka for that. And Ka is equal to 1.8 times 10 to the minus 4. Okay. And you make the X a small approximation. You solve that equation for X. And you get that X is equal to 4.24 times 10 to the minus 3. Right. And so the pH is minus the log of that. And that comes out to be 2.37. Okay. 2.37 is the initial pH. So far, so good?
Are you going to be giving us the KAs on the test?
Of course, yeah. All Kas will be given.
Thank you.
Okay, so now we start adding base. All right. So we got to ask ourselves, what happens? Let's see. Wait, I have a question. Elliot, did you have a question, or did you ask your question already?
I just asked it.
Oh, that was you. Okay, sorry. So the next question we've got to ask ourselves is what happens when we add a strong base to a weak acid? So first of all, when I add base to a weak acid, which equation describes that process? 1, 2, 3, or 4?
3.
3, right? It's a neutralization equation. You're adding OH minus to the weak acid. They're neutralizing each other. They form water and the conjugate base. This is the same thing that we showed here in this, oops, hold on. In this thing, but I just want you to see it one more time because this is so important. When you add a strong base to a weak acid, even though you didn't have a buffer before, you actually create a buffer. All right, so I kind of call this a buffer in disguise, right? Because it's not your typical buffer. Typically, when you think of a buffer, you think weak acid and its conjugate base, or weak base and its conjugate acid, right? But when you add a strong base to a weak acid, look what happens, right? Again, I know we've seen this a couple times already, but look what happens. This reacts with the HA, the acid, right? What does it form? New conjugate base and some water. So the new conjugate base is a product. And now you have significant amounts of both an acid and a conjugate base. So you have a buffer, right? So all along this part of the titration curve, once you start adding an initial pH, we figured out is just the pH of a weak acid. But all along this section right here, you have a buffer. How do you find the pH of a buffer?
Henderson-Hasselbalch equation.
Henderson-Hasselbalch, right? So all you got to do is figure out the relative amounts of the two components. And how you're going to do that? You're going to do that with a Baugh table, right? So you're going to go, let me just get a new sheet of paper here. You're going to set up your Baugh table based on this equation, right? So it's going to be HCHO2 plus OH minus goes to H2O plus CHO2 minus, right? And Baugh tables, you're always going to work in
Moles.
Moles.
moles, right? So that's going to be, and we already calculated the moles here at the beginning, right? How many moles of acid did we have before we added anything? 0.00250, right? So we got 0.00250, and then this is 0 and this is 0, right? Or about 0 anyway, it's close to 0. And then we're going to add OH minus. So this is, let's say this is at 5 mils. Okay, 5 mils of that solution, right? So we got to figure out, okay, how much OH minus have I added at that point, right? So I got 0.005 liters times 0.100 moles per liter, because that's the concentration of the base. So that's 0.00050 moles of OH minus, right, at 5 milliliters. Okay. So we got 0.00050, okay? So this gets reduced as it reacts with that, right? And what does it get reduced to? 0.00200, right? It gets reduced by that amount. This all gets neutralized, and this goes up to 0.00050, right? So now I know my two buffer components, right? And I go, aha, Henderson-Hasselbalch, pKa plus log of base over acid, right? And so that equals 3.74 plus the log of the base, which is 0.0050 divided by 0.00200. Okay, so that's equal to.
Wait, isn't it 3 zeros on the 0.5?
Thank you. 0.00050. Correct. Thank you for correcting me. And that comes out to be 3.74 minus 0.60, which is equal to 3.14. Okay, so at 5 milliliters, have a pH of 3.14. So we add that to our graph, and there it is. Does this make sense? Awesome. Okay, now you can keep doing the same thing at 10 milliliters, right? You would do the same thing, and you would just have, instead of this being 0.0005, it'd be 0.0010, right? And so this number would be a little higher. This number would be a little lower. Okay. And so at 10 milliliters, it'd be 3.56. Now at 12.5 milliliters, something important happens. So let's do 12.5 milliliters real quick. 12.5 milliliters of added OH minus. Notice this is halfway to the equivalence point, right? The equivalence point we figured out was at 25 mils, okay? So at 12.5 mils, here's what happens. Again, same exact thing, nothing really new in terms of how we set it up. We have our bar table, right? We start out with 0.00250, right? The difference is that now we've added 0.00125 moles of that, right? So notice what happens. This goes to 0.00125. This goes up to from 0 to 0.00125. First of all, notice we still have a buffer, yeah? And secondly, notice what kind of buffer this is. It's a buffer that has exactly the same amount of acid and conjugate base, right? When you have a buffer that has exactly equal amounts of acid and conjugate base, what's its pH?
Equal to PK.
Exactly
pKa.
correct, right? Because when these numbers are the same, so this was 3.74 plus the log of 0.00125 divided by 0.00125, right? That's the log of 1. The log of 1 is 0, so that's 3.74 plus 0. So that's just equal to 3.74. Okay, so this is generally the case. So write this down in your notes. Halfway to the equivalence point, the pH is equal to pKa for that titration of a weak acid with a strong base. Okay. All right, and then you can just keep going, and it's still a buffer at 15 milliliters, still a buffer at 20 milliliters, and you can just keep adding these points, right? Keep calculating them. The ratio, this ratio continues to change, right, as you add more base, but it's still a buffer. Okay. Scott.
Isn't that 0.0125 liters?
Here?
Yeah,
This is moles.
it's 12.5.
Remember, this is moles,
Oh, thank you so much.
right? This is all in moles. Any other questions? All right, so notice the different kinds of problems we're working here. First point, where do we work? Weak acid equilibrium problem. All of these points in the middle here between 0 and 25, those are all buffer problems, right? Now we get to the end point, to the equivalence point, right? And now it changes into a different kind of problem yet again, okay? So that's the tricky thing about this is you got to recognize what kind of problem you have at each point. So at pH at 25.00 milliliters added base for added OH minus, right? So let's see. Again, we'll just set up our same bar table. HCHO2 plus OH minus goes to H2O plus CHO2 minus. Oh no. Did I freeze up? We still okay? Can you hear
I
me?
can see you moving your mouse. I can think I can see your hand moving.
Okay. All right.
Still fine for me.
Still fine. Okay, great. All right. So we set up our bar table. 0.00250, right? Now we've added 0.00250, right? Sorry, about zero. Okay. So now what happens to this?
Goes to 0.
Becomes
Goes to
0.
0, right? This goes to 0. Now we're stoichiometrically exactly even, right? We've added just as much strong base as we originally had strong acid. So they completely neutralize each other. In so doing, what do we form? 0.00250 moles of this conjugate base. Okay? So now notice, what kind of a problem do we have at this point?
A weak base.
Weak gas.
A
Oh, weak,
weak-
weak base, sorry.
Exactly, a weak base equilibrium problem. Minerva. Minerva, did you have a question?
Yeah, I did. So for the pre-lecture problem that you assigned us, was that just a continuation of the video? Or are we supposed to like start over?
You know what? I can't remember the problem off the top that they asked that's after the video right off the top of my head. But I think I can't remember. But I can go look at it later. Let's look at that after class. Is that okay?
Yeah, that's totally fine.
Yeah, let's go back and look at that after class. Okay, so now look what we have. We just have a weak base, okay? And not only is it a weak base, it's an ion acting as a weak base. So remember how to solve those kinds of problems, right? That's another problem that we've learned how to solve, you know, when we were looking at ions acting as acids and bases, right? So again, let's go to our 4 best friends here, right? Which of these 4 equations are you going to use for an ion acting as a weak base to find the pH? 1, 2, 3, or 4?
2.
2.
It's equation 2, correct. Okay, it's equation 2. So you're going to apply that equation to this weak ion. Notice I'm using the Ba table here to figure out where I am, right? Where am I in this problem? Now I'm at this point, right? Where now all I have is this weak base. So now though, in order to solve the problem, I actually have to use an ice table, right? So I'm going to write the equation for the weak base, CHO2 minus plus H2O in equilibrium with, what is it? OH minus, thank you, plus HCHO2. Okay. And it's an ice table, and I'm going to work in 1 units.
Concentration.
Concentration. Taylor, did you have a question?
Yeah, I'm assuming this is the exact same format if we were using a strong acid and a weak base.
Correct. Exactly the same.
Okay.
Except at this point, the base would turn into its conjugate acid.
Yeah, but also for the steps before, right? Like the whole
Yes.
graph.
It basically mirrors
Okay.
this, except it starts basic and turns acidic.
Okay.
Yeah.
Okay, cool. Thank you.
Okay, so you have CHO2 minus. What's its initial concentration? It's 0.1, right? Sorry, what was
So
it?
didn't we have to divide what we got on the bar table
sorry,
by the volume?
Yeah, I'm crazy. I'm going crazy. Right. So that's the first thing we got to do. Let's figure out the concentration of CHO2 minus because we don't know what that is, right? We know that we have 0.00250 moles, but we have to divide by the total volume to get the concentration, right? Because we need that concentration for that ice table, okay? So we got 0.00250 moles. Now, what's the total volume at the equivalence point?
Is it 50?
50,
mils.
correct. 50, right? Because you had 25 initially, right? Remember, we started out with 25 milliliters, right? But to get to the equivalence point, we added another 25 milliliters, right? So now the total volume is actually 50 milliliters or 0.050 liters, okay? So my concentration of CHO2 minus at this point is 0.0500 molar, all right? So that's what goes into this ice table. Oh, all right, so you have that. You have 0, 0. It's going to go to the right, minus x plus x plus x. You got 0.0500 minus x, 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 right? Notice it's an equilibrium problem. X squared over 0.0500 minus x is equal to KB, right? KB for this base. But you will not be given KB for the base. What do you usually be given? You'll usually be given Ka for the acid, right? So how do you get KB?
1
KW divided by KA.
Yeah, that.
Correct. Correct. Ka times Kb is equal to 10 to the minus 14. So Kb is equal to 10 to the minus 14 divided by Ka is equal to 10 to the minus 14 divided by, what was it? 1.8 times 10 to the minus 4. And that turns out to be equal to 1.7. Sorry, no, that's wrong. That turns out to be equal to 5.6 times 10 to the minus 11. Okay. So that's what KB is equal to. Now you can make the x a small approximation, right? Because look at this tiny KB, right? And so then I'm going to take x squared is equal to 5.6 times 10 to the minus 11 times 0.0500. And I take the square root of that and I get my x 1.7 times 10 to the minus 6. Okay, does that make sense? Am I breaking up? Oh, okay. So most of you are getting me straight. I'm not breaking up too badly. Certainly much better than last time, hopefully. Okay, very good. All right, so what is x equal to in this case? Let's go back and look. It's equal to the OH minus concentration. Okay, so pH, sorry, not pH, POH is equal to minus the log of 1.7 times 10 to the minus 6, right? That's equal to 5.77, okay? And so pH is equal to 14 minus 5.77, and that's equal to 8.23. So notice what happens. The pH at the equivalence point is 8.23. Okay. Now, notice the pH is not 7, right? Remember when I had a strong acid, strong base titration, the pH was 7. That was an equal match, right? You had strong and strong. Now I have strong base, weak acid. Who wins? The base, right? That's why the pH is a little bit basic. Okay, it's not pH neutral. All right. Does that make sense, everyone?
Yep.
Okay, very good. Now, what happens when we pass the equivalence point? So let's figure out the pH at 30 milliliters. At 30 milliliters, again, we're going to go back to our table that's going to help us figure out where we are, right? We're going to use this equation and then use the Baugh table. So we got HCHO2 plus OH minus, neutralizing each other to form H2O plus CHO2 minus, right? 0.00250 moles, right? Now at 30 mil, and this is right about zero, I'm going to add 0.0030 moles of base, right? Now what happens? Now this gets completely neutralized again. right? This goes to 0.00250 as that gets neutralized. But look what happens. All the base doesn't get used up, right? There's 0.0005 moles of base left over. Okay, so now what kind of a solution do I have? I have a mixture of a strong base and a weak base, all right? When I have that kind of situation, I can almost always, and certainly for all the problems you'll see, you can ignore the weak base and just focus on the strong one, okay? The pH is going to be, when you have a mixture of a strong acid and a weak acid, or a strong base and a weak base, you can forget the weak one and just focus on the strong one. The strong one is going to determine the pH. All right. So how do I get the concentration of this solution? Well, I need to figure out the concentration of OH minus, right? So I know I have 0.000500 moles, but I need the volume. At this point, I have my 0.025 liters that I had initially. How much have I added? I've added 30. Right? So that's plus 0.030 liters. And that's going to give me my OH minus concentration, which is equal to 0.0091 molar, right? So my POH is equal to minus the log of 0.0091, and that's equal to 2.04, right? So my pH is equal to 11.96. So boom, my pH shoots up to 11.96 right there. Does that make sense? What would I do at 35 milliliters? What would change here? Instead of this being 0.0030, it would be what?
3.5.
0.0035.
0.0035, right? So this still goes to 0, this still goes to that, but this, instead of being 0.0005, becomes 0.0010, right? And if I figure out the pH of that, divide by the total volume, I get this next point, which is 12.22. And then if I keep going, I can get the rest of these points, okay? And I just do all those the same way. And there's your entire titration curve, right? Look at how many different kinds of problems we've had to solve here. At the beginning, we had to solve a weak acid equilibrium problem. In the middle, we had to solve a buffer problem, and we had to figure out the relative components of the buffer, the relative amounts of the two components of the buffer, right? Here, we had to solve a weak conjugate base with the ion acting as a base, right? Equilibrium problem, right? And then over here, we had to just figure out the pH of a strong base. So a lot of different things going on to calculate the different points in this curve. Okay, so what's the secret to being able to do these kinds of problems? The secret is to identify where you are, know what kind of problem you're dealing with, right? And then know how to solve that kind of problem. Okay, that's the key. You got to know initially, oh, it's a weak acid equilibrium problem. Oh, here it's a buffer problem. Oh, here it's a weak conjugate base problem. Oh, here it's a strong base problem. Okay, those are a lot of different kinds of problems that we've all done individually, right? We've looked at all those individually in the past, but now they're all lumped together in one kind of complicated titration curve. Okay, and if you can do this, right, you're doing very well. If you understand this titration, you understand a lot of what we've done. So this is a key type of problem to really spend a little bit of time on. And that's why I had you watch it in the video. That's why I'm doing it again in lecture, right? Because this is key, right? This is the key kind of problem that if you can understand this, you're really understanding a lot of what's going on. All right. All right. Let's see if you're understanding. Let me ask you a question. Okay. Well, let's see if I did a decent job explaining this. I always know if I did a decent job by how much You guys, when everybody misses it, then I know I didn't do a very good job. All right, go ahead and try to answer this question. All right. Give you a couple more, another few seconds to pick the answer. You're looking for one of these points, A, B, C, or D, that's in the buffer region. Okay, I think I'm going to end it right there. And awesome. 3/4 of you got that correct. So nice work. It's B, right? This is the buffer region. This is weak acid, buffer, weak conjugate base, strong base, right? It's becoming more basic as you go from left to right. Nice work. Okay. Now, the ultimate question. Try to do one of these on your own. Okay. I'm going to start the polling here. I'm going to give you some time, and I want you to work through this question. You got to find the pH at the equivalence point. Um, just to save you a step, I've given you pKa here, but Ka is equal to 2.88 times 10 to the minus 8.
Does that say 0.288?
2.88 times 10 to the minus 8. That's the value of Ka.
Okay.
So if you have pKa equals 7.54, that corresponds to a Ka of 2.88 times 10 to the minus 8. I'll give you one hint. In order to do this problem, you have to start by figuring out the volume to the equivalence point. Okay, you have to figure out how much volume it will take to get to the equivalence point. So just in case you're getting stuck, I just want to show you the first part of this calculation, and then I'll wait a couple more minutes to show the rest of it. But you, like I said, you need to figure out the volume to the equivalence point. That's a good thing to do right at the beginning, right? So the volume at the equivalence point occurs when moles acid equals moles of base. So you just figure out the moles of acid, right, which is 0.045 liters times the given concentration, which is given right here, right, 0.240 moles per liter. That gives you the moles of acid, right? There's your moles of weak acid. So you're going to need that same exact number of moles of base. So then you go, okay, I have that many moles of base times the concentration of the base. That gives you the volume to the equivalence point. Okay, you're going to need that in just a minute. The next thing you want to do is you want to say, okay, what is the reaction that's happening? Well, as I add a strong base to a weak acid, I get this reaction, number 3, right? So you write it down and you set up your BA table, right? 0.0108 moles of that. At the equivalence point, how much OH minus have you added? 0.0108 moles, right? So this gets completely neutralized. This goes to 0. This gets completely neutralized. That goes to 0. And this goes to 0.0108 moles. So now you think, okay, what kind of a solution is this? And how do I find the pH of this solution? And you see that, aha, this is a solution of a base, right? Of a weak base, right? But it's an ion acting as a base. So you go back to your equation and you say, okay, how do I find the pH of a solution of a weak base? I solve an equilibrium problem using this equation, right? So you apply that equation to this ion and you get OCl minus plus H2O in equilibrium with OH minus plus HOCl, right? And now to solve this problem, you need to solve an equilibrium problem. So you need to set up an ice table. Whenever you set up an ice table, of course, you need that initial value to put in here. Now, can you work in moles in an ice table? No, never, never, right? You can only work in concentration. What does that mean? You have to figure out the concentration, right? So what do? You say, aha, I have 0.0108 moles of OCl minus, right? Divided by the total volume. Well, what's the total volume? I started out with 45 milliliters, 0.045 liters. And now to get to the equivalence point, I've added 0.0432 plus 0.0432 liters, right? That gives me my concentration of OCl minus that I have to use to start this problem. And that's equal to 0.122 molar, right? So that's the value that goes here. It's a long problem, right? That's the one that goes there. And then you got to solve an equilibrium problem, okay? I'll give you one more minute and then I'll finish it. The next step is to finish your ice table. So you know that this is going to go to the right, minus x plus x plus x, right? So you got 0.122 minus x and x and x. So x squared over 0.122 minus x is equal to kb. The next tricky part of this problem is how in the heck do I get kb? Because I was given ka, right? So remember, ka times kb equals kw, right? So kb is equal to kw divided by ka. Right, so kb turns out to be equal to 3.47 times 10 to the minus 7, right? So that's equal to 3.47 times 10 to the minus 7. I make my x a small approximation. I get x squared is equal to 3.47 times 10 to the minus 7 times 0.122. Right, then I solve that for x, and I find that x is equal to 2.06 times 10 to the minus 4. Right? And then I go back to my ice table and I find out that x is equal to the OH minus concentration, right? So then I take minus the log of that, and that gives me POH. So POH is equal to 3.69. Right, so therefore pH is equal to 10.31. Does that make sense? That's how you work that kind of problem. It's a hard one. And it takes some time, but there's no single part of it that's particularly difficult. It's just a matter of working your way through the entire process to arrive at the final pH, right? And not forgetting any of these little steps. Okay, I'm gonna go ahead and end the poll. It went okay. I mean, it's a hard problem. About half of you got it, almost half of you got it. So anyway, if you didn't get it, go back and work this problem again. Make sure you can do this kind of problem. I guarantee you're gonna see this kind of problem on the exam, right? Okay. Any questions on this?
Just how much time will we have on the exam? Same as last time, right?
You have 80 minutes,
And will it be the same amount of questions?
30 questions. So you do have a little bit extra time on this exam compared to the last one because of questions like this. Yeah, yeah, you might be right there. You might be right there about that. If I have too many questions like this, then we'll, we won't have an exam, right? Because I won't have any other questions. So, but I guarantee you will see one question like this. So it's important to be able to do all those parts of this problem. Okay. All right, very good. Any other questions from me before we do our last topic of the chapter and our last equilibrium topic of the semester? Woohoo! We're almost there, folks. No questions? All right. Again.
Oh wait, actually, I do have a question. So we don't have to find the initial pH for that one.
I didn't ask for it, right? But if, if you did, how would you find it? What kind of problem would you have to solve to get the initial pH?
The ice table. Ice
table for a weak acid, correct.
Because we did that on one of the other ones.
Correct. But this was just, so, on the exam, I'm not gonna, each question will be, so there might be one question on how to find the initial pH. There might be one question on how to find the pH at the equivalence point. There might be a question on how to find the pH halfway to the equivalence point, right? There won't be just one question that asks you to find an entire titration curve, right?
Oh, okay.
Okay. Okay, good. So the right answer was E, by the way. Okay, now if you're doing a weak base with a strong acid, just exactly the same, except for the equation you'll be using, right? for the neutralization reaction is this one where this is a base plus the acid, and then you get the conjugate acid on this side. Okay, and everything would just be switched, and you'll get some practice on this in your problem set. But basically, you're going to start out by over here. You're going to work a weak base equilibrium problem, right? We all know how to do that. Then you get the buffer region. The only tricky thing here is for the Henderson-Hasselbalch equation, you always got to use pKa, right? But when you're titrating a weak base like ammonia, you're going to be given Kb, right? So you just got to find Ka and then find pKa. Remember, the Henderson-Hasselbalch equation, you always use pKa, right? And it's always pKa plus log of the concentration of the base over the concentration of the acid, okay? No matter what, as long as you have a buffer, that equation is going to work. All right. And then here, instead of having a weak base like we did in the other one, now you're going to have the weak conjugate acid, right? But it's going to be exactly the same kind of calculation as you just did, but it's going to be the weak conjugate acid instead of the weak conjugate base. All right. And then over here, it'll be acid in excess. All right. But you have a little practice of this in your homework. Okay. Now, there are some acids that are polyprotic acids, and we've seen some of these. Things like, for example, sulfuric acid, H2SO4, or even H3PO4, phosphoric acid, where you have 2 or 3 protons, okay? These acids, right? Remember, sulfuric acid is strong in its first proton and then weak in its second. Right, so they just lose their protons sequentially like this, right? And we talked a little bit about polyprotic acids in the past. I'm not going to have you do a titration of a polyprotic acid. You don't have to know how to do that. But I do want you to know what the curve looks like, right? It's going to look like this. Why? Because you're going to have one endpoint for the first titration and then another endpoint for the second titration. The important thing about this is that the volume to the first endpoint is going to be exactly the same as the volume to the second endpoint. Why is that? Because the moles of acid are the same, right? So it's going to take as many moles of base to get the first proton titrated as it does take the second one to get the second one titrated. All right. So the volume to the first endpoint is going to be the same as the volume to the second endpoint. All right. We're going to not worry about that. And here we are. Here's our last real topic. I'm not really going to cover this last topic. So our last topic for this chapter is solubility equilibria. All right. So remember last semester when we talked about the solubility rules and we categorized ionic substances as being either soluble or insoluble, right? Did everyone remember that? And you had that table of solubility rules. Well, it turns out that things that we classified as insoluble are really a tiny bit soluble, even though we classified them as insoluble, right? So for example, something like lead chloride, we classified that last semester as being insoluble, but really it's more of an equilibrium where the lead chloride dissolves a tiny bit, okay? And this is the equation by which it dissolves. Lead chloride goes to Pb2 plus 2Cl minus. Now, this is an equilibrium, right? So there's an equilibrium constant for it. So how do you express the equilibrium constant? K is equal to the concentration of lead 2 plus times the concentration of Cl minus squared, right? Nothing new here. This is just equilibrium again, right? And that value though, instead of just being called K, for these kinds of compounds, it's called KSP, solubility product constant. All right, but it's the same thing. It's the equilibrium constant for this reaction. Okay. So this table in your book has the KSPs for a lot of different substances. Notice they're all small, right? Because remember, these substances we said were insoluble. that was a little bit of an oversimplification. They're actually a tiny bit soluble. And these equilibrium constants are the equilibrium constants for those reactions in which these ionic compounds dissolve, right? So for example, if I was to look at silver chloride, right, I'd say, aha, silver chloride solid in equilibrium with Ag plus, aqueous plus Cl minus, aqueous, right? And K for that, which we now call KSP for this particular type of equilibrium, right, is just the concentration of Ag plus times the concentration of Cl minus. Are you with me? Does that make sense? I know that last problem was a strain on the brain. Hang in there with me. This isn't too complicated. All right. So just hang in there with me and we'll be finished. Taylor.
Is there such thing as an insolubility constant?
Insolubility? No.
Okay.
No, it's just the solubility product constant. There's no.
Okay. Okay. Cool.
So,
Just curious.
of course, those things that last semester we classified as soluble, right, have KSPs that are huge, right, that are really, really big. So we don't even worry about those. Those go to completion, kind of like a strong acid.
Okay.
Right? Okay. So these are just for these things that were, we kind of considered insoluble, but they're really that tiny bit soluble.
So this is
Okay.
really like the Le Chatner's principle side of it. Le
Pardon me?
Chatelier's.
Yes.
This is like that principle of that. Okay.
Well, there's no Le Chatelier's principle here yet. All it is an equilibrium, right? All we have so far is equilibrium, right? And so if I put this in solution, there's an equilibrium between this and this. But because the KSPs are so small, the equilibrium lies far to the left. But nonetheless, you can still figure out the solubility of something from the solubility product constant, right? Even though it's not very soluble, you can still figure out how much is soluble. So let's do an example like this. And this is the only kind of problem I'll expect you to be able to do for this topic, okay? PbCl2 solid in equilibrium with Pb2 plus 2 Cl minus, and these are both aqueous, right? So we want to find the molar solubility, right? So we say, oh, okay, it's just an ice table. That's just saying what is the equilibrium concentration of these things, right? So the equilibrium concentration we figure out by solving an ice table problem. So this, of course, doesn't matter because it's solid. This is 0, this is 0. This is plus x, this is plus 2x, right? So since that's 0, that's plus x and that's 2x. So then we just substitute into the expression for KSP. KSP is equal to the concentration of lead 2 plus times the concentration of Cl minus squared, right? That's just the equilibrium expression for this reaction. Yeah, nothing new there, right? And so I plug that in and I find KSP is 1.17 times 10 to the minus 5 is equal to x times 2x, the quantity squared, right? So what do I have? 3x cubed is equal to 1.17 times 10 to the minus 5, right? So x is equal to the cube root of 1.17 times 10 to the minus 5 divided by 3, right? And I take the cube root of that.
Wait, why did you do 3x squared or 3x cubed? Oh, because you had to, oh, never mind.
Oops, sorry, my mistake. Thank you. Thank you for catching that. What should it be? This is wrong.
4x squared, or shouldn't it be 4x squared?
Should be 4x, right? 4x cubed. 4 divided by 4. Should be 4, right? Because 2 squared is not 3. I was mixing up that 3 with that 3. So it's 4x cubed is equal to that. Thanks for catching that. All right, so x equal to the cube root of that, and that comes out to be equal to 1.43 times 10 to the minus 2 molar, right? And so x, now the question is the solubility equal to x or 2x? Well, the number of moles of this that dissolve per liter, right, is equal to x, right? 2x is twice the solubility. So that's just equal to x. So that's also equal to the solubility. Okay, let's have you try a quick one. Make sure you're getting this. Oh, this is sorry, this is just the same problem again. Sometimes on these problems, instead of calling it x, they'll call it s for solubility, but it's the same exact thing, right? We substitute in KSP is equal to 4s cubed, take the cube root of KSP over 4, and there you got it. Okay, this is the same problem. All right, here's the one I want you to try.
Is this gonna be on the exam?
Yes.
Okay.
This is the last topic. The last topic for the exam and the last topic for equilibria, and then we'll be done with equilibrium and you'll be over the hump in this course. Megan, did you have a question right now or you want to wait till after this problem?
It's not on the problem, but it's like regarding the material. Will we still have lecture on Wednesday, or is it a review?
Wednesday will be review.
Okay, awesome. Thank you.
Yep, we're going to finish here today, so that's kind of nice. Taylor, did you have a question?
Yeah, it's just kind of on the problem, not like an answer thing. It's kind of just a concept thing. You're able to write an equation like that because it's a solid, right? The KSP equal to the constant, like it's not divided by the product or
Correct, because
the reactant.
right. Because remember, solids and pure solids and pure liquids are not in the equilibrium expression.
Okay, so it's just your products.
It's just aqueous or gases.
Got it. Okay.
Right? Solids and liquids are omitted from the equilibrium expression. Correct. Okay, it's looking really good, you guys. I'll give you 15 more seconds. Looks like almost everybody's getting this one. Okay, I'm gonna stop it there. And the right answer was B, and look at that. Woo! Nice. Love to see that. So really quickly, in case you didn't get it, it's AgCl in equilibrium with Ag plus Cl minus, right? These are aqueous. This is solid, right? So you write the expression for KSP is equal to the concentration of Ag plus times the concentration of Cl minus, right? You set up your ice table, right? And you got 0, 0, plus X. So you got X and X. So that's just then X and X. So you got X squared is equal to KSP. KSP is 1.77 times 10 to the minus 10. So X is equal to the square root of 1.77 times 10 to the minus 10. And that's equal to 1.33 times 10 to the minus 5. Okay? That is our last equilibrium topic. Whew. Oh, I'm tired. That's a lot, right? Okay, but this is totally doable, and you just have to practice, 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 right? Remember, you learn by doing, right? You can't just reread the notes and passively listen to the lectures. I get students all the time. They come to me and say, Tro, I studied and studied and studied, and I still didn't do very well on the exam. What happened? I said, well, how did you study? And they always tell me, well, I reread my notes and I watched the videos. And I'm like, well, there's your problem. That doesn't work. You have to do, you have to answer questions. Remember, chemical education research shows us that recall, remembering, and recalling is what makes you learn, right? You have to actually do the problems and remember how to do them. You have to do them yourself, step by step. So practice, practice, practice. The final's coming up. Sorry, not the final. The next midterm's coming up just in a few days. The best thing you can do right now is practice, practice, practice. We've covered all the material you need for the exam at this point, right? So you should be ready to finish all the problem sets. You should be ready to take the pretest, right? The pretest is a big source of practice for you, all right? Also, if you want more practice, you can go to the study area in Mastering. And in the studying area, there are these cumulative quizzes, right? And you can take quizzes for any chapter you want, right? So you know that this exam is going to cover chapters 16, 17, and 18, right? So you can look and take additional quizzes for those. You can also go back and practice some of the problems that you did before, right? So that's the key. Now, remember, the test is on Thursday. I advise you not to stay up all night studying on Wednesday, right? You also you have 80 minutes to do this whole exam. It's going to be tight. I'm not going to lie to you, right? The timing is tight and it's intentionally tight, right? I'm trying to prevent those few people that might cheat from having too much time to cheat, right? And so the timing is tight. You have to know the material very well, and you're going to have to work through it. So the next couple of days are going to be key for you to make sure you finish off this chapter, understand the material, and then go back and practice, okay? Know that I'm rooting for you guys. I want you all to do very, very well. I'm here to help, right? Send me an email. I'm happy to meet with you on Zoom, all right? In fact, I think I'll do a little session Thursday morning. Let's do, I'll send out an email about this, but I'll do like, so I'll be here, of course, Wednesday. We'll do a review. I'll hang around afterwards for any questions. And then Thursday morning from 9 a.m. to 10 a.m., those of you that can make it, I'll have an additional hour of Zoom that I'll be available, okay? But of course, if you can't make those times, send me an email. I'll make time for you and I'll answer your questions, okay? And help you in any way I can. So also take advantage of our TAs. They're available. I know they're doing a great job. I've heard from many of you about that. So, so get this done. Don't let it slide, because the better you do, the more you work in the next couple of days, the better your spring break is going to be, right? Because you will have put in all the effort, you will have done well, and then you'll be ready for a really nice break, okay? And I think Santa Barbara gets to the red tier tomorrow. So things are going to start opening up even. Won't that be nice? All right. I think I'm going to end today's lecture there. Thank you for your attention. You guys are the best. I really love seeing all of you. Thank you for turning on your cameras, as always. I know a lot of faculty are having trouble with students turning on their cameras, but you guys are great and you're always turning them on. And I really appreciate that. So anyway, have a great afternoon. Study hard. I'll see you all on Wednesday for the final review, and then you'll take the test on Thursday. Again, I'm sticking around if you have any additional questions. but otherwise I'm going to stop the recording and you're dismissed.